Okay, so hello everyone. Welcome to ESSEC seminar series. This is John, the seminar coordinator, and I'm with Miss Kathy Medley. Kathy is our communication specialist, and Kathy and I will be today's moderator. And we are excited to have our speaker, Professor Jerry Mitrovica, joining us from Harvard University. Just so you know, then this seminar is being recorded and will be later published on our YouTube channel. Please feel free to ask questions. You can do this by sending us a message, or you can raise your virtual hand, and we will unmute you. Please allow me to introduce the speaker. So Professor Jerry Mitrovica is currently the Frank B. Berger Professor of Science in the Department of Earth and Planetary Science at Harvard University. He is a recipient of the Rutherford Memorial Medal from the Royal Society of Canada, the Stacey Prize from the National Research Council of Canada, the Oxter's Knapp Medal from the European Geoscience Union, the Jadowski Medal from Columbia University, and the Arthur Day Medal from the Geological Society of America. He is a fellow of AGU, the Royal Society of Canada, and the John Simon Guggenheim Memorial Foundation. He was recently named as a fellow of the John and Catherine MacArthur Foundation. So let's welcome the speaker, and Professor, please proceed.
Thank you, John. I was saying to some of you who were already on that this is a picture of I won't be talking about this today, but this is a picture of a Roman fish tank or piscina, which wealthy Romans built in order to keep the fish that fishermen brought in fresh until they had a chance to eat them. And it turns out that these are really important, provide really important constraints on the way sea level has changed over the last few thousand years. This is work in particular by preeminent sea level scientist Kurt Lambeck at ANU in Australia. Actually, this reminds me that Kurt once saw a talk I gave that was on YouTube in which I said that I wished I had written the paper that he had written on this fish tank, but senior faculty always read a paper every so often that they wish they had written. So in my talk, I say that. The problem is he saw the talk. So now every time he submits a paper, he sends it to me and says, here's another paper you wish you had written. So I wish I hadn't have started that idea. Okay, so I'm going to be talking to you about sea level change. I have the main goal of this talk in some way is to try to give you an idea how solid earth scientists, how geophysicists are providing kind of an important debate or important contributions to the discussions of global climate change. Sea level or solid earth science enters into climate change through studies of sea level change of the kind that I'll talk to you today, but also in studies of how bedrock elevation, for example, below polar ice sheets changes with time. I'm going to try to do something slightly different in this talk. I'll present some results, but before I do, I'll provide a kind of short primer on each of the topics that I'll be discussing, because I'm going to be looking at sea level that varies for timescales of millions of years right up into the present day and global change processes. And in each of those cases, I'll start with a 5-minute sort of primer. In some ways, you could sum up my whole career in some way by this term, a eulogy for eustasy. Eustasy is this now arcane concept that geophysical processes, where it's the melting of ice or the change in the spreading rates of plates, will produce uniform sea level changes globally. My work has really been focused over the last few decades, in particular, on showing that this isn't true, that all geophysical processes produce a geographic variability in sea level. And that variability should be embraced because it always tells you something quite important about the underlying process. And I'll try to give you a few examples of why that is true. But I'm going to start with a pop quiz. This is something I've done in the last couple of talks I've given. I'm going to ask you, what would happen to sea level in Chesapeake Bay if enough ice melted from the Greenland ice sheet to raise global sea level 5 meters? That's most of the Greenland ice sheet, in fact. If you were to catastrophically collapse the Greenland ice sheet so that if the world was a bathtub, sea level would rise by a global average of 5 meters, what would you actually see in Chesapeake Bay? Now, the answer to that is you'd see about half of that global average. You'd see about 2.7 meters. Okay? So then I can ask you the same question about the West Antarctic ice sheet. What would happen to global average, what would happen in Chesapeake Bay if you melted enough material from the West Antarctic, and that's effectively the entire West Antarctic, to raise global average by 5 meters? Well, in that case, you would see sea level rise by 6.7 meters, significantly greater than the global average. The difference between what you see in sea level at Chesapeake Bay in those two scenarios is a factor of 250%. Right? And so I hope by the end of this talk, I'll describe some rather counterintuitive results in sea level physics that explain this difference. The importance of the difference should be quite clear to anyone, right? If you're an urban planner, you should not care directly about global average sea level rise. You should care about local sea level rise and the processes that will cause that local sea level rise to differ from the global average. I'm a sort of ice age modeler in a way. A lot of my work is focused on ice age processes. This is a slide of oxygen isotope variations over time, over the last 3.5 million years. This is in thousands of years. And variations in oxygen isotopes, for those who don't know anything about this sort of topic, give you a measure of how ice volumes have changed with time, right? I'm going to look at 3 specific cases. Here we are today. Here we are 3 million years ago. Here are the ice age cycles you hear so much about. Here is this peculiar, enigmatic change in ice age cycles called the mid-Pleistocene transition, where these more rapid 40,000 year cycles prior to that period transitioned into a period in which, our current period, in which ice age cycles lasted for about 100,000 years. I'm going to talk about sea level problems involved with geological records at 3 million years ago and 400,000 years ago. And I'm also going to be talking about the modern world and tide gauge records of sea level change in the 20th and 21st century. Okay. So I'll start with this. MPWP stands for the Mid-Pliocene Warm Period. This was a period in which, if you just believed oxygen isotopes at face value, you would argue, because these oxygen isotope values are higher than the present day value, that sea level must have been higher in the mid-Pleistocene than it is today, right? And so let me talk about why that's important, why the inference of how high sea level was in the mid-Pliocene is important, even for modern climate studies, right? The mid-Pliocene was a period in which atmospheric CO2 levels were similar today. There's, of course, uncertainty, but they're around 400 parts per million. Temperatures were elevated relative to present-day values by a couple of degrees Celsius. That's important because it's those temperatures we would obtain by the end of the current century if we were to even stop any emissions of greenhouse gases, further emissions. You'd get another degree or 2 of temperature rise just by equilibrating to the present levels of CO2, right? Estimates of sea level change 3 million years ago, based on a number of different geological markers, but in particular, a 3 million year old shoreline along the US East Coast that are called the Orangeburg Scarp, has been used to suggest that sea level then was about 25 to 50 meters above present sea level. And that's a very, very troubling conclusion. Because if you really needed polar ice sheets to have melted sufficiently to raise sea level 25 meters higher than today, you would have been assuming then that the Greenland ice sheet, the GIS, the West Antarctic ice sheet were essentially entirely gone. And there was also extensive melting of the East Antarctic ice sheet That's problematic because we generally think of the East Antarctic ice sheet as relatively stable, even in the modern world. But this would indicate that this period of protracted ice age warmth, you would collapse the East Antarctic ice sheet. And the question is this inference robust? Well, here's the Orangeburg Scarp. I wanted to give you a picture of it. Now, it turns out, I'm not a geologist, but it turns out that the peculiar thing, a scarp is just an ancient beach, right? And that scarp tends to be at an elevation on the order of 50 meters above present-day sea level in that area. It's called the Orangeburg Scarp here in South Carolina. So I just pulled this off the web recently, a geological map of South Carolina. And the Orangeburg Scarp, I think, although I'm having trouble reading these labels, is this line here between this sort of orangey color and the red and green color, right? That's the Orangeburg Scarp. If you walk along that scarp, a beach, you're on average 50 meters above present-day shoreline, which is down towards your southeast here, right? One thing I forgot to mention, and it has important implications for modern climate, is it is quite common when you are using modern ice, ocean atmosphere ice coupled climate simulations. One of the ways in which you test the robustness of those models is you put in what you know about the Pliocene, and you argue that you need to get this 25 to 50 meters. So that means there's two really important implications of looking at what sea level was like 3 million years ago. One, by trying to understand, was it true that the East Antarctic ice sheet would have had to collapse? And two, that sea level is used to tune modern climate simulations. So in both ways, this is important in getting to the bottom of how high sea level actually was during this period. Right? I'm going to talk to you about a process called dynamic topography. This is something that actually even involved my PhD thesis so many years ago, the discussion of dynamic topography. Dynamic topography represents vertical plate tectonics. The same processes that move plates sideways, and plate tectonics is largely thought of as a horizontal process. We have seafloor spreading, continental drift. But the same processes and forces that move continents around laterally also move plates up and down. And that process has come to be known, at least in the last few decades, as dynamic topography. And I'm going to talk to you about why we believe, a group of my colleagues and I, that the Orangeburg Scarp, this feature that's often been used to estimate what global average sea level was like 3 million years ago, has been highly contaminated by this process. But I need to start, well, let me start with the debate first. Let me go instead straight into kind of a primer now on dynamic topography, right? What is dynamic topography? How do you see it if you're a geologist walking around North America, for example? This is a beautiful picture that I actually used in a paper that's now 20 years old. It's from an area called Strike Valley, Utah. Some of you may have seen. These are old beach levels, of course, old sea levels. There's been very, very few deformation of those strata. They've just been either uplifted or sea level has gone down. They are a kind of central area in the debate. I'm now using somewhat arcane terms. The debate was called eustasy or epeirogeny. This is a picture here of what the Earth's surface looked like about 80 to 100 million years ago. Okay? At that time, almost the entire western half of the United States was underwater. This actually has a name. It was called the Western Interior Seaway. And since that time, sediments filled that area. Since that time, these features have emerged out of the water, right? The water is gone, obviously. So the question is, does this reflect eustasy, that is, the rise in sea level and then a subsequent fall in sea level? Or does it represent what the old continental geologists, very famous geologists, Slosh, Speed, and others that some of you may have heard of, would argue, no, this has nothing to do with global sea level. This is the continents being deflected downwards, and then the continents being deflected upwards. What I would now call dynamic topography, vertical plate tectonics. Which is it? Right? Well, let me go a little bit deeper in this primer. This is the first paper that I ever wrote on dynamic topography, and it was an attempt to explain this seaway that existed in the Western United States and Canada, where I'm from, 100 million years ago. What this paper argued is that subduction zones, so this is a kind of cartoon cross-section of a subduction zone where you have one plate descending below another plate. So consider this to be North America in this picture. Okay. As that plate descended, it drove flow under North America downwards, right? And those normal stresses acting on the base of the plate here acted to drag the continent downwards. The continent would then flood, fill with sediments, and when that subduction ended, when the driving force for that subsidence ended, the whole thing would pop up. The argument in this paper is this process, this dynamical topography associated with what is, after all, a part of the convection cycle in the Earth's mantle, is what explains the appearance of these uplifted strand lines in Strike Valley, Utah. Not everyone agrees with that, of course. There's still some that believe it's a sea level, a changing global average sea level that caused that feature, right? Okay, let me give you an idea of how one goes about to model these things. Here's just a profile. I'm looking through a profile through sediment packages along the US, on the western half of the US. So this is the topography of Western North America. So if you know that, it tends to increase towards the west. Here's a 500-meter topography, 1,000 meters, 1,500, 2,000, etc. So as you walk from the middle part, the Midwest of the United States towards the west, you will encounter higher and higher topography. And in cross-section, this is what this tilting of the continents did. Something caused the continent to tilt downwards to here, along that profile. And there's a Canadian, I'm not going to try to guess which states those are. I think that's Wisconsin, but I'm not absolutely sure. This filled with sediments. Later on, when the dynamic process of forces plate down ended, those sediments were uplifted, and you get this topography that increases towards the west. You know, for those of you who are football fans, I'm not really a football fan, but Denver football stadium is Mile High Stadium. And most people think, well, that's because Denver is near the Rockies. But Denver being a mile high has nothing to do with the Rockies, really. Denver being a mile high is due to this process. You've uplifted sediments upon which Denver sits by ending this process that tilted the continent downwards, okay? Why did it go up? I said subduction underneath the west coast of North America led to subsidence because it dragged the overriding plate, the North American plate, down. And for those who know a little bit about plate tectonic reconstructions, that subduction ended about, well, time, let's say it started to end around 50 to 60 million years ago. And I'm just going to show you a cartoon. The plate that was off the west coast of the United States at that time was the Farallon plate. The Farallon plate is largely gone. But here is a reconstruction of the evolution of that plate system over the last 40 million years. So here we are, you continue to subduct the Farallon plate. Eventually, you start subducting the boundary of the Farallon plate. You produce the San Andreas Fault here. There are still remnants of the Farallon plate. At time zero here, this little remnant of the old Farallon plate is the Juan de Fuca plate that now would cause problems in Seattle, Vancouver, etc. And to the south, it's the Cocos plate, right? But if we go back from 50 million years ago on, it was the Farallon plate until the subduction zone began to subduct this mid-ocean ridge between the Farallon plate and the Pacific plate. So the timing works, right? When we talk about this subsidence, that is the flooding of Western North America, that occurred during the time of active subduction of the Farallon plate off the west coast. The uplift of strand lines that you see here began as soon as the Farallon plate began to disappear and subduction ended under the west coast, okay? That's what caused this tilting. But that's a story I'm including because there is importance even to the East Coast story here. how could the Farallon plate that's subducted under the west coast have any influence on what's going on in the east coast? Well, I'll try to explain that. Right? This is a seismic image. It's been converted from seismic velocity anomalies into density anomalies here. Under North America, you can kind of see the North American continent here. Here's Florida. This is the same thing, but it's viewed slightly differently so that you can get the kind of sense of what's going on better underneath the North American continent. This is a present-day snapshot of density differences that occur in the mantle under North America. This large blue area here, that's an area where seismic velocities are faster than average and densities are higher than average. It turns out, lo and behold, that blue region is none other than the Farallon plate that's subducted under the west coast of the United States from 40 million years ago, about 10 million years ago, right? That's the present location of that slab. It didn't just magically disappear because it left most trace, very little trace left on the surface of the Earth. What's been happening since that time is that North America has drifted over the location of that, of the Pacific, let's say. And so the Farallon plate is now situated directly under the east coast of the United States. The little green arrows here represent the flow that is being produced by the descent of that Farallon plate into the mantle, right? As that is going down, you have flow downwards along the Farallon plate, but it also produces return flow that thrusts hot, low-density material upwards to impinge on the US East Coast, right? With some colleagues, I've even written a paper. There were sort of these enigmatic seismic events called the New Madrid seismic events that happened in Missouri over 100 years ago, 200 years, nearly 200 years ago. We argued that it was the state of stress in the plate and the crust associated with this flow was an important element of those seismic events. But what does this flow do? What has it done to the topography of the US East Coast? And here's my next, and I think my last video. What this is it's a video of a reconstruction of mantle flow here. This is a cross-section through the mantle from the surface down to the core, and this is a map of changes in elevation since 30 million years ago along the US East Coast as that Farallon plate here, this blue plate, subducted downwards, and this hot stuff impinged upwards. Now, this is a little bit of a lie, this image, because I'm showing it going forward in time from 30 million years ago to today. But what we actually do to create these videos is we take the snapshot that seismologists provide us and we roll the film backwards. We use the equations that govern mantle convection over time and we reverse them in time. We go back from 0 to 6 to 12 to 8 and 30. But then I run the movie forward to show you the evolution of topography. And what you're seeing on this United States East Coast is that the descent of the Farallon plate causes this interior region, has caused this interior region of North America to go downwards by hundreds of meters over 30 million years. And it has caused this coastline to be pushed upwards. So geologists would say, and there's lots of geological evidence for this, that the east coast of North America has tilted up towards the west because of dynamic topography. And this is not a minor effect. Over 30 million years, we're talking about hundreds of meters of deflection of the elevation of that coast. So what has it done to the Orangeburg Scarp along this, over this 3 million year period? Remember, I told you that that scarp has an average elevation of 50 meters or so. That is, that scarp now sits 50 meters above present sea level. But now I've told you that dynamic topography is actually lifting the continent on the US East Coast. And so it might be contributing to this elevation of the Orangeburg Scarp. How much is it contributing, right? Well, it is contributing nearly everything, right? And to show you that, what this plot is a reconstruction of where that movie that I showed you would place the 3 million year old shoreline. That's given by that blue-white trail here. This is, of course, the present-day coastline of the Earth, this gray line here. Okay. The transition, oh, I'm sorry, I reversed it. This line here, the white and blue here, represents where the Orangeburg Scarp actually is today, where it is in sort of geographically. The green to blue transition here from dark green to blue represents where we reconstruct the shoreline, where we would place it by taking into account the dynamic topography, the uplift of the continent that's happened in the last 3 million years. So what you see is that over large areas of this scarp, with some misfit over Georgia and Georgia particularly, and Florida, you can reconstruct the location of that scarp very well, not taking into account any melting or any kind of melt from the East Antarctic ice sheet. And so the conclusion of this paper is we cannot really conclude robustly how high sea level was 3 million years ago as a consequence of ice sheet melting, unless we take into account the dynamic topography that contaminates shorelines of 3 million year old age. So it's a kind of an example of, strangely, how an understanding of plate tectonics and plate tectonics processes has influenced our understanding and our sense of the stability of polar ice sheets in the progressively warming world we're entering into. Okay, so now let me move to the second part. This is MIS 11, marine isotopes. Forget that, that's just jargon that Ice Age people use. This is an interglacial, much like the present day. Okay? Whenever you're up at this level, here or here, I hope you can see my cursor, here and here, you're at a time between these large-scale glacial cycles, right? So, Ice Age and climate scientists study these interglacials for obvious reasons. They are periods that are seen as analogs of our present interglacial. So the question that is always asked in these studies is, during a period like MIS 11, which was a protracted period of Ice Age warmth, right? During this period, what happened to the polar ice sheets? We can try to understand what will happen to polar ice sheets by running climate simulations, and that's certainly an important thing to do. Another way we can try to assess the stability of these ice sheets to periods of warmth is to look to the geological record and ask them, well, what happened then? And what happened then? The two interglacials that are the focus of most of that literature are MIS 11, 400,000 years ago, 4 glacial cycles ago, and MIS 5E, or the last interglacial, about 120,000 years ago, the last interglacial prior to the present one. So why is MIS 11 often a focus of paleoclimate research? Well, it happened about 400,000 years ago. It turns out, for those of you who know a little bit about Milankovitch theory, it was a period in which it sort of spanned 2 precessional cycles. All that means is that it turns out that this was the longest interglacial of probably the last 1,000,000 years, not only the last 500,000 years, right? So it's lasted much longer than the present interglacial has lasted, right? Okay. So that's important, and that will become important, right? Now, there have been discussions of sea level at MIS 11, and in particular, there is a long-standing debate that started 20 years ago and continues to today that discusses the geological record of sea level in Bermuda and the Bahamas. In both of those regions, there is evidence from all sorts of proxies for sea level. You can read them here. Fenestrae rich. Fenestrae are these little bubbles you see when you walk along a beach today near the shoreline. What you see is these percolating bubbles that come up, these air bubbles that rise from the sand, right? Those are usually, if you see them in older rocks, you can usually assume that the shoreline was very close to where those bubbles were. So there's a whole host of different records here, right, that suggest that sea level in Bermuda 400,000 years ago was 21 meters higher, and sea level in Bahamas was consistent to that, about 20 meters higher. Again, what does that actually mean? What are the implications of that for ice sheet stability? If you melt the Greenland ice sheet and the West Antarctic ice sheet, as much as we would expect them to melt in a warming period, you could get up to 8 or 9 meters. You cannot get 20 meters, right? So that additional change from 9 or 10 to 20 has been associated with collapse of the East Antarctic ice sheet. And that's what's led to a huge debate in the literature. This is an example, by the way, of one of those records. This is one of those records of sea level. This is at a location 20 meters above sea level. And I probably can't see, but there actually is a person there who I hope is wearing a high SPF factor. But that person is sitting on evidence of sea level that reached 20 meters and dated to 400,000 years ago, MIS 11, in the middle of that long island in the Bahamas called Eleuthera. Here's the debate. There is a group that believes that that 20 meters does reflect very accurately ice sheet melting, and has argued that it would require partial collapse of the, in addition to the West, the East Antarctic ice sheet. There is another group altogether that says, no, not at all, right? That these features that you're associating with the high sea level are really just mega tsunami deposits, right? And they go through one after the other of these features and argue why you might be misinterpreting a stable sea level for something that just came by after presumably a large earthquake, produced a large tsunami, and sea level washed over these landscapes, right? So we were interested in looking into this, and this work was done with Mo Ramo, really absolutely brilliant paleoclimate specialist at Columbia University. What Mo and I wondered is there a geophysical process related to the Ice Age that may have contaminated, just like dynamic topography contaminated the elevation of the Orangeburg Scarp? Is there a geophysical process that might have contaminated the elevation of these ancient sea level markers in Bermuda and the Bahamas, right? So I'm going to now give you a primer on Ice Age sea level. So this is my second primer. It's work that I focused a lot of my energies on over the last 20 years. This is a prediction. This is a computer simulation. I'm going to take you through it and try to explain what all these colors mean. But this is an image of the sea level change that you would expect during an interglacial if there was no changes in ice volume that was happening. So this is a dynamic effect on sea level that has nothing to do with continued melting of ice. It's important that I emphasize that, right? So this is the kind of image you would get in any interglacial, even at present day. This is how the amplitude might change a bit, but this is how sea level is changing due to the last ice age cycle today. Even though we're 6,000, 7,000, 8,000 years out of the last ice age cycle, sea level is continuing to change today because of this process, and it can change during MIS 11 too, this earlier interglacial. The physics is identical, okay? But that should give you a hint of why these sorts of figures are important. If you're a modern sea level person and you're looking for evidence of ice sheet melting in the modern world in sea level, you need to take into account this signal. You need to correct the modern sea level record for the signal due to ongoing ice age effects. And you know, when I was a graduate student and starting to produce these sorts of images, very few people cared about this sort of thing. But it's become more important more recently in the last decade or so as people realize that this sort of figure is exactly what you need to correct tide gauges and satellite signals of modern sea level for the contaminating influence of the ice age before you say anything about what the modern sea level record tells you about ice sheet melting. Okay, that's a lot. That's the longest sentence I've ever made in a talk. Okay, so let me try to give you an understanding of what this all means. I should point out that these dark reds and dark blues at high latitudes are off the scale bar of this plot. The paper that I'm taking this figure from is a paper that was focused on the equatorial regions here. And so we didn't really care about saturation in the north or south, okay? But so everything here at low latitudes is within this plus or minus half a millimeter per year range, but these dark red regions are sea level falls of up to a centimeter per year. A centimeter per year, right? 10 millimeters per year or so. Let me give you a sense of what's going on in this very complicated looking plot. Well, okay, in these regions here in the near field, so I'm going to talk about these blues and reds here that are near the polar regions, right? When an ice sheet sat on the Earth's surface, as it did over Canada and northeastern US, a larger ice sheet existed over the Antarctic, an ice sheet existed over Scandinavia, etc. It caused subsidence of the crust below it. When that ice sheet melted, that crust began to uplift or rebound. This is something that you've probably heard about. It's called post-glacial rebound. It's a kind of iconic phrase in Ice Age sea level. It refers to the rebound of the crust after ice sheets have vacated an area. Now, I should point out that sea level, in terms of the geology of sea level, represents the depth of water, that is, the height of the sea surface relative to the sea bottom. So you can change sea level either by changing the height of the sea surface or by changing the elevation of the crust, just as I showed you on the US East Coast with dynamic topography, right? So if the crust here is rebounding, moving up, what you will see is a drop in sea level or fall. And in these regions, that fall can reach amplitudes of a centimeter per year. Today, it continues. So let me give you a picture of that. This is a photograph taken from, this actually mislabeled. This is a photograph taken from the northern part of Hudson Bay. Richmond Gulf is that small island, which you may or may not see on my figure here, right? But regardless, this is a very classic picture. If you fly over Hudson Bay, all the shorelines of Hudson Bay have this feature. The Canadian geologists who study these things call them flights of raised beach terraces. What this means is, this is an ancient beach. What happened was sea level fell because that crust uplifted. The next beach formed, and then the next beach formed, and the next beach formed, and so on, until you get this series of parallel shorelines, ancient shorelines, and you're down here at the present shore. This is a geological manifestation of this uplift process of post-glacial rebound, right? Okay. Now, for our purposes, as I'll tell you, that's going to be less important than what happens just outside these regions in these blue areas. If you've caused subsidence in areas that were covered by ice sheets, you cause the crust outside those areas to bulge upwards. If I take a spherical object that's relatively incompressible and I press down on one location, around my thumb, I will get a bulge because you have to conserve mass. If you're pressing down somewhere, you have to push up somewhere else. So as these ice sheets cause subsidence, here, around the periphery in these blue regions, they caused uplift of this, what's known as the peripheral bulge, okay? And when those ice sheets began melting and causing post-glacial rebound, that led to a rise in sea level in these blue regions because now the crust is falling. So the depth of ocean water between the sea surface and the crust increases. Sea level is rising. So today, let me go back to this thing. Today, even if we were doing nothing to climate, even if we never increased greenhouse gas emissions above pre-industrial levels of 260 or 270, whatever they were, right? Even if we didn't, sea level would still be rising along both coasts of the continental US because those coasts happen to be on the peripheral bulge of the Laurentide ice sheet. And as those bulges subsided, sea level would rise. I often, in my classes on sea level, ask an exam question like saying, why is it difficult, or why is there a shortage of archaeological sites along the US East Coast dated to 2,000 or 3,000 years? And the reason for that is sea level's been rising along that coast, and the magnitude of that rise, I haven't even told you, could be up to 3 or 4 millimeters per year. So over a few thousand years, you've had a sea level rise of you could have 5 or 6 meters of sea level rise along that coast. So those archaeological sites would now be underwater. Okay, so that's a peripheral bulge. Let me end this primer on Ice Age research by talking about what happens well away from these regions in the far field, even though it doesn't really have much relevance to what I'm going to get to. Because these peripheral bulges are subsiding, water has to move away from these low latitude regions up to the regions that are vacated by the peripheral bulges. And that's what this cartoon is showing. As these bulges subside, for example, off the US East Coast and West Coast, water enters into them, and then the level of the whole ocean drops downwards, which means that in the far field, and this island, by the way, should be connected to the plate, it shouldn't be sitting there floating, would see a sea level fall. Imagine, for example, you're at the edge of a large swimming pool, and somebody takes an object out of one side of that swimming pool. Even if you're really far away, you're in an Olympic-sized swimming pool, 50 meters away, you're going to see the level of that water drop as water enters to take the space of the object that's been removed. And that's what's happening here. And that process is called ocean siphoning. And it can contribute sea level fall up to 0.5 millimeter per year or so. And it produces features like this in the equatorial Pacific. This is a picture of a coral at Malden Island, this dot here. This coral's dead now. There's a live coral underwater, but this coral, the top of this coral is about 3 meters above sea level and it's dated to about 5,000 years of age, right? And so if you take that 0.5 millimeter per year of sea level fall and multiply 0.5 millimeter per year by 5,000 or 6,000 years, you get 3 meters. So if you were sitting there on a beach sunning yourself somewhere in the equatorial Pacific, you'd probably be skeptical. But these features, which are pervasive in the equatorial regions, uplifted beaches, exposed corals like this, that exposure isn't associated with any local effect. It's associated with the siphoning process, a process that really originates from things happening near the poles of the Earth as water moves away from them. Right? But all of this is happening because over the last 5,000 years, you haven't been melting any ice. Okay? Okay, so that's a long primer into Ice Age research. What does this have to do with the story that I was telling you about the interglacial 400,000 years ago? Well, Bermuda, which is here, and the Bahamas, which is here, this Long Island here is Eleuthera, both sit on the equatorial, on the peripheral bulge of the Laurentide ice sheet. So there's where the crust is still rebounding, or was rebounding through MIS 11. And over this region here now, sea level was rising across the interglacial because the peripheral bulge was subsiding. I'm not really, yeah, I can annotate. So I'll need that in a second, right? But what does this mean? It means that during MIS 11, sea level in a location like Bermuda or Bahamas would be progressively rising over time during that interglacial because of this process, which has nothing to do with melting of ice sheets, okay? So we can ask, what does this mean about what you would see in sea level? Well, since sea level is rising during the entire interglacial, if you see a record of sea level in these areas from MIS 11, it probably dates to the end of that period because sea level continued to rise throughout that period, right? But remember, we're in an interglacial today. And so the question is, if I ask you, what is the height of a beach that's 400,000 years old in Bermuda relative to the shoreline today? That's a tricky question, right? Because you're really asking, during MIS 11, sea level rose, but sea level also has risen during the present interglacial. So the height of a 400,000 year sea level marker on Bermuda will depend on how more extensive the sea level rise was during this period relative to the present interglacial. Let me try to annotate something. I hadn't thought about this. But imagine this is an annotation of the sea level rise that occurred during MIS 11. And here we are 400,000 years ago, and here's the sea level rise. That sea level rise would be less extensive than the sea level rise, and my cursor has disappeared now, during MIS 11, because MIS 11 was much longer. Remember when I introduced it, I said that MIS 11, the interglacial 400,000 years ago, was a much longer interglacial than anyone in the last million years. For that reason, sea level rose in the last interglacial, MIS 11, significantly more than it has risen during the present interglacial. And so what you really need to do is correct the height of that beach 400,000 years ago for the difference between these two yellow lines here. And unfortunately, I cannot see my cursor. It has disappeared. So we're going to have to try to find my cursor, I think. Is there any way the moderator can get me out of my screen share?
Yeah, let me take it from you. And then I can take, so I took the screen share away. Let's just restart it.
Yeah, let's do it again. So all I have to do is screen share again, right?
Yeah, yeah. You should have the button in a second.
Yeah, there. I see it. Hold on. Share. I knew that annotating was going to be a problem, but okay. I did what I needed to do. Are you seeing my screen now?
Yep, it's good.
Okay, great. Thank you.
That's normal.
Okay. So what we have to ask is, what correction do we have to make for those sea level heights relative to account for this dynamic effect that sea level was rising during that period, MIS 11. It had risen more during that period than in the present interglacial. And it turns out that that correction happens to be about 10 meters, right? So here's the observation that I talked about, the observed elevations of 20 meters. It turns out that about half of that elevation is associated not with melting of ice sheets, but rather with this dynamic effect, the peripheral bulge subsidence in Bermuda and the Bahamas. Now, that lowers your estimate of sea level rise during those periods to about 10 meters from 20. That's not good news. It still means that the West Antarctic ice sheet and the Greenland ice sheet collapsed entirely during the marine isotope stage 11, 400,000 years ago. But those sea level records from that interglacial do not require any additional melting from the East Antarctic ice sheet. Okay, so last part of the talk is the modern, which in some ways is perhaps the most relevant to what the audience is interested in. Modern sea level changes are estimated through a number of processes. We have tide gauge records. These are relatively low-tech devices that are spread around the Earth's surface, right? And have measured, in some cases, sea level for the last few hundreds years. So the power of tide gauges is they've been there a long time, but they're sparse. On the other hand, we have satellite altimetry, which has been measuring sea level changes over, since the early 1990s, right? Much more complete sea level record over the oceans, although they don't go from pole to pole, they're still much more complete, but much smaller time scale, right? Okay, tide gauges are the typical, are the main record that one uses in estimating 20th century sea level change, right? They're pretty low-tech devices. You can think of a cylinder with a ping pong ball stuck on a pier. As the water goes up and down, the ping pong ball goes up and down, and you have to measure the sea level change associated with that, right? Now, here's some example of tide gauge records to give you some idea of how noisy they are. But they have a lot of limitations. They're sparse. You have many more tide gauges in the northern hemisphere than you do in the southern hemisphere. Very few tide gauges in the open ocean. There are huge data gaps when tide gauges were down, right? They're very noisy. So it is difficult. And using tide gauges to estimate 20th century sea level is a problem that requires statistical sophistication, because this ocean is noisy and you're pulling out a relatively small signal. I've included this figure just to show you that since around 1985, the number of tide gauges in the northern and southern hemisphere is decreasing. The reason for that is as storms damage these tide gauges, they're no longer replaced generally because people say, well, we have satellites, we don't need these tide gauges. So this record is soon moving towards extinction, okay? Now, when you use tide gauge records, when they've traditionally been used to measure 20th century sea level change, this is a record of such an estimate, right? Well, it combines various estimates, but embedded in this is tide gauge record. Traditionally, the published estimates of tide gauge based estimates of global mean sea level rise, the average sea level change over the last 20th century range from 1.5 to 2 millimeters per year, okay? But there's an assumption that is made in those studies, and that assumption is I can go to every tide gauge record that I have around the Earth. I can look at the rate of change over the 20th century that I get from that tide gauge, and not all tide gauges will give me a good estimate of that, but I get all of those rates that I can find. I just average them out. That's not exactly what's done, but on broad brush, that was what's done. The assumption in that study is that when an ice sheet melts, sea level rises uniformly, because I'm just taking the average of the rates here, right? And I'll emphasize that assumption in a minute or so. But now I come to my original pop question, and I say to you, what would happen to modern sea level if the Greenland ice sheet collapsed? What if we melted enough from the Greenland ice sheet to raise global average sea level? What if the Earth's ocean was a bathtub where you turn the tap on and things more or less go up uniformly, right? Well, if you believe in that model, you would see 1 meter everywhere, right? But in fact, that doesn't even come close to happening, right? When you melt an ice sheet, at least, there's more than this, 3 things happen that I'll talk about. One is you're definitely entering meltwater into the ocean. You are increasing the mass of the ocean. There is no doubt about that, right? The second thing that happens, I've already alluded to, and that is that as you melt an ice sheet, the crust will rebound. The dashed line here represents the location of the crust and the surface of the Earth when you had an ice sheet this big, and the red represents those locations when you melt it down from here to here. So as you melt it from here to here, the crust uplifts a little bit, okay? That's the second thing that happens. The third thing that happens is, believe it or not, this is counterintuitive. The ice sheet exerts a gravitational pull on the ocean around it. You might say, well, that's got to be pretty small. The moon and the sun might cause meter level changes, but the moon and the sun are much further away from the Earth than the ice sheet. When an ice sheet melts, the gravitational pull it exerts on the ocean decreases and water migrates away from the ice sheet. That's what I'm trying to show here by going from the dashed line to the red line. You're literally moving water away as you melt that ice sheet because the ice sheet no longer gravitationally attracts the water as much. The combined effects of this migration away from a diminished ice sheet and post-glacial uplift of the land, both of those things, the drop in the sea surface and the rise in the land, produce a sea level fall. So this might be counterintuitive, but it turns out close to a melting ice sheet, and I haven't told you what close to means yet, sea level falls. What does close mean? Close is about 2,000 kilometers or 1,200 miles if you're in the imperial system, right? Here's an image of a simulation in which enough ice was melted from Greenland that if the bathtub worked, sea level would have risen uniformly by a meter. The red zone here represents that zone in which sea level will actually fall due to the melting of the Greenland ice sheet. But you pay the price. As you move further and further away from the ice sheet, sea level will rise by progressively greater amounts. There's other effects here that distort from that simple idea, but the general trend is as you move away from Greenland, you get a sea level rise. So in a place like Tierra del Fuego, here in the southern South America, in Chile, sea level will rise by about 30 to 40% higher than what you would expect from the bathtub. Close to the ice sheet, the effect is very dramatic indeed. If you were to raise sea level, if you were to melt enough ice off Greenland to raise global average sea level a meter, sea level near the shoreline of Greenland would actually fall in excess of 10 meters. Right? This is not a small effect. The rebound and the gravitational effect act in tandem to drop sea level by an order of magnitude greater than what the bathtub tells you that sea level would rise in the vicinity of that ice sheet, right? Okay. Now, each ice sheet will have a distinct geographic pattern of sea level change. The pattern here represents the pattern you get if you melt the Antarctic ice sheet. So here, the red zone is the region in which sea level would fall due to the melting of that ice sheet. And as you go to darker blue colors, you get a rise. There's no doubt this is counterintuitive. I once gave a talk to Dutch scientists, and I told them that they were in much bigger difficulty, this was years ago, if the Antarctic ice sheet melted than if the Greenland ice sheet melted. And I tried to explain to them that sea level wouldn't do much at all if Greenland melted. And you can imagine their skepticism. But this is just Newton's law. This isn't complicated modeling here, right? This is just applying, you know, m1, m2 over a squared, right? It is not something with a lot of tunable parameters, okay? So there are no doubt that these fingerprints establish themselves as ice sheets melt. And let me give you an idea of why that's important. This is from a paper published about 15 years ago of the rate of change in sea level in millimeters per year at a whole bunch of sites around the globe, shown by these squares here. These were at one point no longer considered gold standard sites to do sea level research, right? And these were the rates that were measured. These are European tide gauges here. This is New Zealand, North America here, South America, and US East Coast here. And you see this variability. When this variability was first seen, the way one dealt with it was just to take the average, as I said before. And in this case, you take the average, you get about 1.6 millimeters per year. So if this is all you use, you would estimate that global average sea level rise in the 20th century was about 1.6 millimeters per year, and you would forget about this variability. And in fact, that was so deeply inbred into the thinking of the time that features like this one, the fact that all European tide gauges tended to show less global sea level rise in the 20th century, or local sea level rise in the 20th century than the global average. That was called the European problem, right? What could be producing that? But inherent to that phrase is your belief that as these ice sheets melt, just as this cartoon is showing you, sea level would rise uniformly. But this gives you an idea of what happens if you add fingerprints of Antarctic and Greenland melting, as well as other fingerprints I haven't talked about, thermal expansion of the water and a few other things together. You can explain this entire geographic variability in sea level by embracing the idea that all of the processes that are producing changes in modern sea level produce geographic variability in that sea level. Nothing works the way this cartoon produces. So by adding these fingerprints together, you can get a much better fit to this variability. But more importantly, the variability tells you something really important. It tells you, by looking at that variability, you can say more than what sea level was doing in some global average sense. You can actually talk about and actually infer where that water was coming from by understanding the distinct, unique patterns or fingerprints that each of these ice sheets have, right? So I'm going to end with just a couple of minutes and talk to you about a reanalysis of 20th century tide gauge records by two of my graduate students, Carling Hay and Eric Morrow. I had no intention of going through the statistical side of this, just to say that they use a technique called Kalman filtering, which allows you to use tide gauges and to bridge this sparsity, the fact that you don't have records here, by combining measurements of sea level where you have them with models of sea level, like the fingerprint models that I've talked about. when you think about it, if you're using tide gauges to estimate 20th century sea level, and you're just taking the average, what you're actually saying is that you have no information whatsoever about sea level down here in the South Atlantic, where you don't have tide gauges. You know nothing about sea level there, but in fact you do. Because if you know what the tide gauges are telling you, and if the physics of your models is accurate, you know that sea level can't go up by more than X or down by more than Y here if you have measurements at relatively close by tide gauges. It doesn't even have to be close by. So combining these ideas, combining the ideas of fingerprints in common smoothing with tide gauge records, you're much better able to get a robust estimate of what global average sea level rise was in the 20th century. This is just, this is sort of showing off a little bit. What this is this was a demonstration that you could actually accurately predict what sea level happened in New York and other tide gauge sites. And that's the prediction is by the shaded region here. The data is the red. Even if you don't include them in your simulation, that is, you do all the statistical analysis, not including these tide gauge sites, and then you say, well, now let me predict what actually happened in New York or Zemlya or Champlain Kamena or Finland, etc. Data that I didn't use in my simulation, in my statistical work. And you can see that you can fit them very nicely indeed, right? Well, what do those tide gauge, what does that reanalysis of tide gauge records taking into account the fingerprints tell you? Well, it tells you that sea level rose significantly lower than had previously been estimated in the 20th century. Instead of the 1.5 to 2 millimeters per year, now this paper, the paper by Hay and colleagues, has been reproduced. Now, these results in at least 3 papers. The new estimate of 20th century sea level rise is 1 to 1.1 millimeters per year, in fact. So the rise that actually happened was 30 to 50 to 60% lower than we expected. Now, as you can imagine, this was jumped on by a number of people because people said, well, you see, so climate modelers or people interested in sea level got it all wrong. Sea level was much lower than they thought in the 20th century. It wasn't as bad as they thought. But that was completely, that was changing the moral of the story. Nobody, once you got satellite data in the late 1990s, all efforts to estimate sea level since then are consistent. They estimate a sea level rise of 3 to 4, now currently close to 4 millimeters per year. Nobody disagrees with what sea level's been doing over the last 20 years. If Kay et al. Have reduced the estimate of what 20th century sea level rise was, that what they're effectively doing, what that paper is doing is showing that the acceleration of sea level from the 20th to the 21st century was significantly higher. And these are estimates of acceleration. No need to worry about the amplitude here, or the unit here, but you can see that by reducing the estimate of 20th century sea level rise, you have in fact increased the estimate of the acceleration of sea level rise from the 20th, 21st century by a very significant amount indeed. The Hay paper was not a good news story. In fact, it was a very bad news story. Acceleration was much higher than previously thought. This is an attempt to reinforce that just by showing you, by looking at that statistic and saying, I'm going to take 15-year running averages of sea level, and I'm going to bin them, right? And when you do that, you notice that the last 5 15-year running averages are all the most recent running averages. And that's just telling you the same thing that this thing is telling you, is that sea level has risen as you've gone from the 19th to the 20th century. And that's always a story about sea level in a way. Sea level is always a story of an increase over time. I've been involved in studies. In fact, I started with a picture of Roman fish tank, remember? And those fish tank studies have shown, as have other studies subsequent to them, that sea level rise in the 20th century of 1 millimeter per year could not have been occurring at the same rate over the last 2,000 years, right? Because those Roman fish tanks would have been submerged by several meters of water. And you can see from that picture that they were not, right? So sea level rise in the 20th century, and there is a study that was published a few years ago, I was a co-author, in a statistical sense, you are confident at better than 95% accuracy that in the 20th century, sea level rose by more than it did in any of the preceding 20th centuries. Well, now we look at the 21st century, and you are confident now at the same level of accuracy that sea level rise we've seen in the last 20 years was not the average sea level rise of the 20th century. So now I can go back to end this talk by looking again at this slide. When I said, how much does sea level rise if Greenland melted enough to raise global sea level 5 meters or West Antarctic melted enough? And it gives you an understanding now of why the sea level rise that the University of Maryland will see in Chesapeake Bay the damage caused by that sea level rise will depend very much, the amplitude of that sea level rise, where that ice comes from. Because if it comes from the Antarctic, you are going to suffer far more flooding than if it comes from Greenland, right? Because the sea level rise in Chesapeake Bay, if the Antarctic ice sheet melts relative to Greenland, will be 2.5 times higher. And that's, in a sense, the moral of the whole story, that you cannot continue to look at global average sea level. All sea level is local. And I'll end there, and I'm sure I have gone over time.
No worries, Dr. Mitrovica. Thank you for that talk. I do have a number of questions for you already, but just so everyone is aware, you can raise your virtual hand and I'll unmute you, or you can chat me a question or send it in the Q&A and I will read it out loud. So the first one that I have is from Suresh Basu, who asked, how valid is it to take a single rate and multiply it by several thousand years, especially when rates driven by any kind of rebound are expected to change?
Well, so when I discussed, that's a very good question. If we only had the Roman fish tanks, for example, that's a marker of sea level 2,000 years ago, but it tells you something about the integrated sea level change from 2,000 years on, but it doesn't tell you what happened 500 years ago or 1,000 years ago. It just tells you what the net change was in sea level from the times that those Romans built those fish tanks to the present day. But we do have records. I haven't shown indication of that. We have records, again, the US East Coast is ground zero for those. It's a group of scientists that have done a kind of superhuman job of producing what are called high resolution records by looking at marsh records along the US East Coast and now, at other locations around the globe that allow you to track sea level over the last few thousand years. The importance of the fish tank story was it was one of the first ways in which we could provide evidence that things had changed in the 20th century, right? But these records from marshes track sea level through that whole period. And when I said that we are statistically significantly confident that 20th century sea level rise was greater than any century of the previous 20, right? It wasn't based on the argument from the fish tanks alone. It was based largely, but not exclusively, from these marsh records. So we do have measures of sea level in each of those intervening centuries. Just like in the 20th century, we have tide gauge records that span the entire 20th century. So we can measure how sea level changed in any decadal period during the 20th century, and we can compare it to what it did in the last century, right? If I give a public talk on sea level, I'm generally asked 3 questions. I'll only mention 2 here. One is that sea level has risen, but has been rising at the same extent for thousands of years. And then I talk about the fish tanks, or I talk about the corals I showed you earlier, right? Another somewhat aggressively asked question is, well, okay, it's changing, but it hasn't accelerated. And I can tell you without a shadow of a doubt that sea level has accelerated. We are now in the 3 to 4 millimeter range. 20th century was a 1 millimeter range. So both of those arguments against sea level being an important factor in climate change or in anthropogenic effects on climate can be easily repudiated. But as a scientist, I have to be careful. We have records that span that whole 2,000-year period.
Thank you. I have two questions from Mike Evans, and I'm going to mispronounce some of the words in this question so that you can actually read them as well. So I'll try my best. So Mike Evans asks, but the isotopic change in foraminiferal 018 MPWP versus modern tell us there is some melt from terrestrial ice, right? Is it consistent with the corrected SLR estimates?
Yeah. That's a really good question too. And you need to ask one of my former students, now professor at UC Santa Cruz, Tamara Pico, to speak to you. If you look at those oxygen isotope records, Mike, and you can recognize, and here's how we've tried to get to the question of how accurate are oxygen isotope records as proxies for sea level. That's ultimately what I think you're asking, right? And clearly from the sophistication of your question, you know that there are temperature effects that play a role, right? Oxygen isotopes will change both because of the temperature of the water and the volume of ice sheets, right? So to answer that question, we've been focusing on the last ice age cycle. And what Tamara's done is she's looked at sea level from geological markers of MIS3, which is a period 40,000 years ago, when you were in the middle of a large oscillation in sea level. And she can show you that sea level inferences or estimates of global average sea level based on oxygen isotope records, depart very significantly from what is possible from the geological records of sea level change. In fact, let me put it this way. At 40,000 years ago, oxygen isotope records would tell you that sea level was 80 meters lower than present, on its way to about 130 meters lower than present at last glacial maximum. And what Tamara has shown through a series of studies is that sea level could not have been more than 40 meters below present. And so you can be off by very large factors. My suspicion, Mike, is that how far you're off really depends on the time scale of the variability, and that, but my main conclusion would be, yes, in some general sense, oxygen isotope records give you a sense of ice volumes and sea level, but when you're looking at in fine detail, they do not. And so I would be skeptical of any sea level records that are determined by just using a proportionality factor and multiplying the oxygen isotope records. I hope that answers your question, but I know there's a lot to that question, but I'm happy to follow up.
Mike also left a second question. Oh, and he just said thank you in the chat. His second question is, for the Pleistocene results, do they agree with the forum isotopic changes?
Yes, yes. So the question is, if I look over the last 2,000 years, I think that's what you're asking, or, well, that would be Holocene. So maybe I'm not. So in Pleistocene, if you're asking over the entire Pleistocene, the last few million years, the answer is no. As I've said, there's they track each other. There's no doubt about that, right? They track each other. But the magnitudes you would get by using a naive proportionality constant would be off, and off significantly, right? Over the last few thousand years, when I'm talking about those marsh records, etc., the variation in oxygen isotope records does, and I'm trying to remember this from a table rather than memory, does reflect more accurately the variation in sea level over that period. But remember, over the last few thousand years, you also don't have a lot of ice melt, right? And temperatures aren't changing much. So until you reach the 20th century. So you're in a period where not much is changing. And in that case, I think both oxygen isotope records and sea level records are showing the same sort of constant level of sea level.
Thank you. And the next question is from Paul Marvin. He asked, are you aware of any boat-based LiDAR systems or other modern technological advancements beyond satellite observations to monitor sea level change over time?
Yeah. So again, another great question, all of them. Sea level is a noisy data set. When I showed you those tide gauges, you could see that, right? There's a humongous up and down. These things are varying. And remember what we're trying to pick out of that noisy data set. We're trying to pick out sea level changes, secular, long-term sea level changes of like 1 millimeter or 2 millimeters or 3 millimeters as it were now, right? That's a lot lower than the tidal range. It's a lot lower than changes in wind-driven sea level, right? What's in the field is known as dynamic sea level, right? So you are really trying to pick out a relatively small signal. A lot of the fingerprint, the first paper that I think was persuasive on fingerprints, I'm coming back to your question, Paul, but the first was not looking in the modern, it was looking in the paleo, where there are events like a pulse event in sea level 14,000 years ago when sea level rose 20 meters in a few hundred years. In that case, all of these other effects like expansion of the ocean due to warming, dynamic effects would be minuscule compared to the melting effect. And fingerprints have been used in a really interesting way. But in the modern, you're pulling a couple millimeters per year out of a tidal range of 1 meter. So how do we do that? It isn't, the methods that show this most promise aren't methods that look at the top of the ocean, but at the bottom. And let me explain why that is, right? What people, and the first idea of this was described by a former postdoc of my group, Mark Thomas and Chris Hughes, when they were working together in England. But they made the following argument, which I thought was ingenious. It was another one I wished I had come up with myself, but I didn't, right? They said that the best way to measure sea level changes associated with melting is to go to place down on the ocean bottom pressure gauges. And here's why. If you're at the ocean bottom, those pressure gauges, the ups and downs of the ocean associated with dynamic effects on pressure are muted at the bottom of the ocean, right? By the time you get to the bottom of the ocean, the pressure change that you see because of those is more muted than it is than the up and down of sea level at the surface would suggest. But an even more important thing that you avoid is thermal expansion, because if you're at the bottom of the ocean and the water is expanding because of temperature changes, that will have no effect on bottom pressure, right? You're not increasing mass, you're just spreading it out. And so they argued, and I think it was an ingenious argument, that if you really want to see these fingerprints quickly, the best way to do it, and there's an effort underway to try to do this, is to forget about tide gauges sitting at the top of the ocean and their noisy data set, forget about satellites, which face the same problems of large-scale oscillations in the sea surface and pulling out a very small signal. Go to the bottom of the ocean, you'll have a much less noisy data set that isn't sensitive at all to thermal expansion, and you will inherently isolate from that record, using that record, ice melting effects. I think it's just a great idea. The problem is technical, Paul. So they know how to put pressure gauges out there. They're outside, the pressure gauges are at the bottom of the ocean as tsunami warning systems, right? When you see a blip in pressure, it might signal that you have a tsunami that's going to build in amplitude as you hit the coast, right? The problem with those bottom pressure gauges is that they have a drift, a long-term drift. They don't have a stable background, and that doesn't matter, right, for tsunami, because all you want to see is a blip, a short timescale blip. But if you're interested in a long-term sea level trend, you want bottom pressure gauges that don't have a drift. And my understanding not being in the engineering world of sea level, is that that is proving to be a very difficult thing indeed.
Thank you. Also, there's a request from Christopher Schumann in the chat. He asks for the reference to the reduced 19th, 20th SLR referenced at the end of the talk to be provided.
What is that reference? Can you, let me just see the chat.
It might just be me, but Christopher, if you're still here, if you could clarify which reference you're talking about. We also have a verbal question from Suresh, so I'm going to unmute them right now while Chris can.
Yeah. So if you tell me what it sounded like there was a paper published that you wanted me to comment on, but let me know what that paper is, and I can tell you if I know it, and I can comment on the conclusion. I don't see it. I see a couple of things in the chat, but I don't see that.
I think they might just be messaging me. I think that might be the default. Mike says the paper that described the acceleration of SLR in the 21st century, last slide or so. And then Eric says, I think that paper is Hay et al.
Yeah, so that's right. So that's the, well, no, that can't be, because the Hay et al. Paper didn't use satellite laser ranging, right? So that's altimeters, basically, right? It's not quite, right? So there are a number of papers that have talked about detecting acceleration. Tide gauges also show it. So I would say, all I could say without looking at the paper is that I think now that there's consensus in the community that there are a number of papers that have I think in a statistically significant way shown acceleration. You know, everybody who was working in the late 20th century, 1990s, the big effort was to see acceleration. Everyone understood that sea level was rising. The next question was, is it accelerating, right? That was a more interesting question. So there were some early papers published in the early 2000s. Well, I don't know, it's close. But there's consensus now, given this kinds of data you have. All you have to do is compare Hay to SLR estimates of the last 20 years, and you're left with the only conclusion you can have is that there's been a significant acceleration. But I'd be happy if you send me an email or something with a specific paper. I'd be happy to give you my thoughts about it.
Great, hope that helps, Chris. So poor Suresh has been waiting a really long time, so I'm going to unmute them so they can ask their questions. Suresh, you are unmuted.
Hi, thank you. Yeah, that's okay. Could you go back a couple of slides to a nice cartoon you had explaining the reason why, if you have a melting ice sheet, the land will rebound and there's a gravitational effect? There were like dotted lines. Well, I can ask with this one as well. So my question is, this is an equilibrium picture, right? So in reality, let's say you have a sheet of ice that melts over 50 years or 100 years, how long before the land rebounds to reach this equilibrium?
Oh, Jerry, you're muted here.
I'm sorry, I muted myself.
I unmuted you. Yeah, I unmuted you. You're good now.
Okay, so I was just going to say another superb question. I mean, there's several elements of that question that are worth commenting on. The first is simply the timescale over which an equilibrium pattern will establish itself. That's the main thrust of that question, right? And there was a debate, right, over that. I mean, the idea was, and I should say, if I didn't, and I don't think I did, that these calculations basically, water goes where gravity tells it to go instantaneously. And so the question being asked is that true? Is that redistribution of water instantaneous, or does it take a long time? And so after the first fingerprint papers were published, the conclusion was that it could take decades. But very soon after those papers were published, it was shown, and I haven't read them for 3 or 4 years, but I'm happy if you send me your email to look at them again and send them to you. But there were a series of papers published that showed no, because of mixing properties of the ocean, that these patterns would establish themselves very quickly indeed on a timescale of weeks, right? So from a tide gauge sense, and certainly from a geological sense, instantaneous is the way to go, but that wasn't understood right away. There was this debate as to how long before water would leave Greenland and pile up, as this slide shows, in the southern Atlantic. But now the consensus view is subannual, certainly, and that's an important thing to know. The second thing that's interesting about your question is you're placing fresh water into the ocean, cold fresh water, when you melt Greenland or melt the West Antarctic. So, and it sounds like the person who asked the question is quite up on this sort of thing, but you're doing what ocean atmosphere climate modelers call a hosing experiment. What they do is they say, what is the effect on ocean circulation and then on climate writ large of, for example, in this top slide, actually throwing all that cold water into the North Atlantic, right? And will that alter ocean circulation sufficiently to change sea level? And the answer is that's still an open question, but it's an extremely important question, right? Because it is quite possible, for example, that putting all of this cold fresh water into the North Atlantic is going to alter the Atlantic meridional overcirculation, this overturning circulation, the large scale, global scale circulation that in one limb moves up and down the Atlantic. And if you change that circulation, you're changing ocean circulation driven sea level, which is known as dynamic sea level. The reason that's still a question that people wonder about and are looking at is that the first hosing experiments did something that was a little bit unrealistic. They put all that fresh water and they spread it out over the North Atlantic because the resolution of the climate models didn't allow them to do anything. But we know that water or meltwater that's coming out of Greenland is coming out of ice streams, right? These very localized holes, essentially. You can, in that case, the term hosing experiments makes more sense, right? And the question of how those very localized inputs of cold fresh water will alter sea level is still a research level question. It's not something that I do because I don't run those kinds of models, but it is a question that's going to be quite important. In the past, it was thought to be important because, well, wait a minute, what happens to climate and temperatures if you disrupt the Atlantic meridional overturning? That's one phase of that question. The other important aspect of that question is if you're changing ocean circulation, you're changing atmospheric circulation, you're changing sea level, and what's the size of that signal? Now, that said, there is a limit to the size that signal could be, but we haven't reached that limit even close so far in the 20th and first few decades of the 21st century. So there may be another fingerprint out there that we're going to develop in the next few years as we do these accurate hosing experiments, and that's the ocean dynamic fingerprint.
Great. Okay, I have one more question for you in my queue from Santiago Gasso. He says, what is the role of thermal expansion, contraction of the ocean in the general sea level exchanges you discussed? Are these thermal timescales comparable to the ice rebounding scale?
Okay, so on the ice rebounding, I'll answer the question both from an ice age point of view and the modern. In the ice age, from last glacial maximum, which was 20,000 years ago, to the Holocene, to 4,000 or 5,000 years ago, when all that ice melted, global average sea level rose 130 meters. There have been attempts to estimate how much the thermal expansion would have occurred over that period, and none of those attempts is significantly greater than a meter, right? And so during the ice age, where you're fluxing large volumes of ice, thermal expansion would have been a minor contributor. In the modern, that is not so, right? In the modern, in the 20th century, when I say the tide gauges, now there's a consensus view through the analysis of tide gauges that global average sea level rise was 1 to 1.1 millimeters per year, right? Up until 1990, it is quite possible that thermal expansion dominated that signal, right? Post 1990, we are certainly entering into a world now where ice melting dominates. There was always glacier melting throughout that period, but ice sheets, Antarctic and Greenland in general, of course, there's variability in this, are thought to have started melting significantly. And I'm not talking about glaciers that surround Greenland. I'm just talking about the ice sheet itself and the Antarctic until the 1990s. So the consensus view is that in the 20th century, thermal expansion, at least prior to 1980-ish, was a significant and perhaps even dominant contributor to the sea level budget. As we've moved into the 21st century, that's not going to be true. By the time we move to the end of the 21st century, where most projections say 0.5 meter to 1 meter of additional sea level rise global average, that will be dominated by ice melt. It won't be dominated by thermal expansion. So we're in a period of transition. But in the modern world, thermal expansion is important. And so when I showed you this picture, and I included this fit by incorporating fingerprints of melting, the reason why that fit is preliminary is that it doesn't include a realistic fingerprint for thermal expansion, and that fingerprint must have been important, right? All it shows you is that you can capture the variability. Whether this particular combination is the combination that produced that variability, we don't know until we have thermal expansion. And we're never going to have it in the 20th century to the accuracy we need, but we have it far more accurately now because there was an international program called the Argo program, which you may or may not be aware of, but it was a program where on the order of 1,000 floats were placed out onto the ocean. They're out there now, and each day they descend down the water column of the ocean and then come back up to a certain depth. They don't go right to the bottom. And they measure temperature as a function of depth. And through those measurements, we have a far more accurate measure of changes in the thermal state of the ocean and thus sea level change due to thermal effects than we're ever going to have for the 20th century. That's over now. And so to some extent, I think we've done all we can in the 20th century by arguing, no, the global average rate was lower. The records weren't sufficient to do more, but going forward into the now and in projections, and I've certainly written proposals arguing that, okay, now we have much more tools at our disposal, right? We have not only the typical sea level measurements, tide gauge and satellites, right? We have those. We also have Argo floats. We also have GRACE gravity measurements, which are monitoring the mass of the ice sheets. And together they will provide us with a very accurate sort of real-time monitoring of sea level. And that's what you're going to need, of course, if you want to project forward in time. Most projections forward in time now, I'm going to answer a question you didn't ask, but I think it's an important addendum. Most projections forward are still projections of global mean sea level rise. When I said sea level is thought to rise 0.5 meter to 1 meter by the end of this century, that's global average. But if there's any lesson that I've given you from this talk, it's, well, okay, but that's not really going to tell me what I have to do in Boston Harbor or Chesapeake Bay. And the variability in sea level can be so extreme that the global mean sea level rise projections are going to become somewhat irrelevant to that story. The much more important story is the variability if you're going to deal with hazards. And for that, you're going to need to really get an accurate measure, not only of the geographic variability, but improve that even more by using gravity measurements of polar ice sheet mass changes using IceSat, which is a satellite system that basically is measuring changes in ice sheet height as a function of time. You're going to need to put all these together, not only to have sort of sea level at the large scale, but understand the processes and the different ingredients. So I guess I could say that we know the ingredients, we don't know how they come together to produce the entire recipe, but we're getting there by all of these incredibly accurate, unprecedented accuracy geodetic measurement systems.
Well, thank you, Dr. Mitrovica, for answering all of our questions and giving us this great talk. And thanks, everybody, for participating so much.
Yes, going so long. That was
no worries, no worries. I mean, we also have a recording of this talk, so I mean, people can always fast forward. But anyway, thank you so much, everybody. We will be back next week for our seminar series continues. So thank you.